Hello, everyone. This is Giacomo Beccaria speaking, and I would like to welcome you to the new event of the Hypatia Colloquium series. Just to remind you, this is a series dedicated to early career astronomers. Hello, everyone. This is Giacomo Beccaria speaking. Sorry, I would like to welcome you to the new. Yes, sorry, I had my YouTube channel was broadcasting. Sorry about that. So I would like to welcome again to the new event of the series. Today we have two young early career astronomers who are selected. I would like to remind you every time selected through a very competitive process. So congratulations to them. And I'm also thankful to the two chair of today, Simon and Joshua, who are currently ESO students. And thanks for chairing. You will see them in a minute. Just the technicalities. As you know, you can make questions to the speakers at the end of the talks. Of the two talks by using the internal chat or by raising your hand. In this case, the moderator will ask you to make the question yourself to the speaker. For the people that are on YouTube, you can make a question using the online chat, or if you want to make the question anonymously, you can also use a web form that is available on our pages. You fill the form, you send it, it comes directly to us, and then we pass it to the moderator, and then the question is passed to the speakers. Please be aware that there is a 20 seconds delay between the event as it happens on live and the event as it is broadcasted on YouTube. So take that into consideration. But still, if you're watching on YouTube, please also post the question on the live chat, because anyway, the speaker will be able to answer if there is not enough time. They will be happy to and there will be the possibility to answer afterwards. And also, please go to our web pages where there is the program available. On the program, you can click on the title of the speakers, and you can see all the speakers, the picture of the speaker. So if you click on the title, you can download their CV, so you can get to know them better and see the exciting sciences that they are doing and the career they are going through in this time. So with that, just the last technicalities. This for the people, especially that are attending from Zoom, please be aware that the event is live broadcasted on YouTube. And if you are comfortable with that, please leave the event. And you can still follow the event, of course, online. Having said that, I would like to then give the word to Simon, if you are there, so you can introduce the first speaker of today. And thank you very much and enjoy the event. Hello, Simon.
Thank you, Giacomo. So our first speaker is Aishwarya. She's a third-year Impress PhD student working at ESO, and she'll talk to us about the Quasar Feedback Survey. So I'll hand it to her.
Thanks, Simon. So let me start by trying to share my screen. Okay. Could you please confirm everything looks fine?
There is, yeah, that looks good.
Okay, great, thanks. All right, then, good afternoon, everybody, and thank you to everybody who joined in for listening. And I would like to begin by thanking the organizers for giving me this opportunity to present my work. So today I want to talk about my results from the Quasar Feedback Survey, basically focusing on how I think the radio jets, the radio jets are causing these multi-phase outflows and affecting the host galaxies. The work is of course possible thanks to a lot of collaboration and support from my supervisors, Chris and Vincenzo. So before I get started, I want to briefly introduce myself. So I'm Aishwarya Girdhar. I'm from New Delhi, India, where I also did my bachelor's. And then I came to Europe as part of this amazing master's program called Astromundus, which was giving me a great opportunity to do every new semester in a new university and new country. Super grateful to this. And now I'm doing here, and I'm here as an Impress student. All right, then. So we get started. So why do we actually study the black holes? Now we know that most of the galaxies now have this supermassive black hole residing in the center. And we know, thanks to the gravity collaboration, that there is a black hole residing in our own Milky Way galaxy in the center. And also now we have this snapshot of the black hole from the EHT for the M87 galaxy. So, and also for the 2020 Physics Nobel Prize, this was awarded for a study of black holes. So basically all these together point to the fact that the study of black holes is actually gaining a lot of importance. And with this, I bring you to another definition of the black holes extending to the active galactic nuclei. So in the state where they're actually very active and accreting a lot of matter, releasing a huge amount of energy, they're called AGNs, or active galactic nuclei. And the most luminous form of these, or the highly accreting form of these, is what we call the quasars. Now, this energy that's being emitted can come in various forms, such as jets, radiation, accretion disk winds. And this actually points us to this interesting question of how this energy is being emitted and how well is it actually interacting with the interstellar medium in the galaxy and affecting its host galaxy. And this interaction is something we also call the AGN feedback. So let's try to understand AGN feedback using this very nice schematic on the left. So what the schematic is actually showing us is that in order for the black hole to grow, it needs to accrete more gas. And in order for the galaxy to grow, it needs to form more stars. And for both these processes, they need gas, which comes from the same gas reservoir. So basically, when one thing is using this gas, it's directly, indirectly impacting on the other thing. So AGN feedback is essentially understanding how black holes and galaxies that host them grow together or evolve together. So on the plot on the right, I am trying to show what this AGN feedback, what do the cosmological simulations predict about AGN feedback. And this plot very nicely summarizes this, but in order to explain it, I will just call the y-axis to efficiency of star formation. So you can see here that especially in the higher mass category for galaxies, we actually need an AGN impact to reduce the formation of stars in order to match the empirical relationship that is expected. So in a way, the cosmological simulations are mandating the feedback from AGNs. Now, this actually brings us to this another question of, is this impact just negative in the sense that is it only reducing the star formation, or is it also, can it be positive? That is it promoting star formation, or maybe it's not affecting its host galaxy in any way and then there is no feedback. So what do we actually know from galaxy simulations? Let's take a look at this. There are various ways in which you can inject energy into a galaxy. So one form of this is through a quasar thermal injection, which can cause a galactic outflow. Now, this simulation on the left actually predicts that this would lead to no rapid impact on the disk or on star formation. And then there is this other mechanism, which is injecting energy through a low power radio jet and causing a galactic outflow. Now, this simulation actually predicts that there would be a considerate impact on the disk and also on the star formation. Of course, this impact would depend on various things, properties of the jet, for example, the power of the jet and the inclination, and also on the properties of the disk. Now, there are other ways as well to inject energy. But just to present broad ideas, I wanted to discuss these two forms of simulations and what they predict. And I will come back to the jet simulations in a bit. All right, so with this brief introduction, there are some key questions that we already identified in this area. So firstly, what drives these outflows and turbulences in quasar host galaxies? Is it the jets, the disk winds, or the radiations? Then what impact do these outflows have on the host galaxies? And finally, what are the properties and drivers of the multi-phase outflows? Now for today, I want to focus on these two questions, and I want to present some results based on my recent work. Okay, now having asked these questions also motivates me to introduce the Quasar Feedback Survey. The survey is led by Chris Harrison, and there's a very nice summary in Jarvis 21, which I would totally recommend you to take a look at. But for now, briefly, this survey is a sample of 42 quasars, which are at a redshift, low redshift of 0.2, and they're all bolometrically luminous. The quasar in itself has a multi-wavelength data ranging from various different wavelength ranges. But for my study, I'm basically using data from MUSE, ALMA, and VLA, which I will shortly show you. So if I may draw your attention to this plot on the right, The blue contours and the blue data points actually show all the AGNs at a redshift of less than 0.2. Now from these, we make a selection at a very high bolometric luminosity, which is shown by this line, by this dotted line. And then we try to have like a nice coverage of all the FWHM of O3. So a good range of the FWHM, so that we have why O3, because O3 is very useful for studying outflows. And by having a good range, we also kind of try to cover the whole sample space. If you take a look at these color maps that codes these stars of our sample, you will see that most of these objects are radio quiet. So having said that, I want to kind of underline the fact that these objects stand out to be pretty normal in a way, but hence they still show some very interesting features, which I will show to you in a bit. So some key features of the QFEEDS survey are that firstly, it having been taken at such a low redshift, it gives a great sub-kiloparsec spatial resolution, which makes it super useful for an integral field spectroscopy. And then secondly, because it's in this high luminosity regime, it actually, all these targets fall in a regime where the outflows are more prevalent, so it's easier to spot them or more probable to see them. Okay. Having introduced the survey, I bring your attention back to the main questions, and now I would like to show you some multi-phase measurements from MUSE and ALMA. How I plan to show this is by first showing a case study, a very detailed analysis for one of the galaxies, and then I will show a brief overview of the wider sample. So the first galaxy that I would like to show is this, which is at a redshift of 0.1. It's bolometrically luminous. And what I show in this panel is basically an optical continuum, which we get from MUSE. Now, this actually helps us study the stellar kinematics. And then on the right, I show you the O3 emission. This is also from MUSE, and it's color-coded for the different velocity slices of the O3 emission. Also on this plot, you will see in purple contours is the CO3 to 2 transition, which is an observation from ALMA, and it helps us trace the molecular gas. So basically now we can study the stellar, ionized, and molecular gas. And then on the left, I show a zoom in of the very central regions of the galaxy, which also reveals the presence of these black contours, which is actually tracing radio continuum from VLA. And this is actually a radio jet, which is low in power. And having made some inclination estimates, we know that it's very much inclined into the disk of the galaxy. That is, it is almost in the plane of the galaxy. So another way to present this data is through these short video clips at the bottom. So on the left, it shows just moving through the velocity space through the MUSE cube, showing the ionized gas, and on the right, the same thing for the molecular gas. You can see that it's super interesting to see it in this way, because as you move from one velocity end to the other, you can see the galaxy kind of blowing up when it reaches the O3 emission. Okay. Now, what did we actually do is to present very briefly. So we divided our galaxy into different regions and using Voronoi binning. And from each region, then we extracted the spectra for ionized gas using O3 and molecular gas using the CO3 to 2 transition. And then for every emission, we had to make a complex model. So multiple Gaussians were fitted, as you can see on the left and the right for ionized and molecular respectively. And then we finally used this combined model that follows the data in order to get 2 estimates. So for a proxy of velocity, we use the V50, and for a proxy of sigma, we use the W80, which is also a proxy of the FWHM. V50 is actually an estimate that you go from left to right in the emission line, and you stop where it covers about 50% of the flux integrated under the line. And W80 is this division between V10 and V90, where about 80% of the line flux lies. So using these 2 estimates, we draw some conclusions, which I will show you now. And before that, we also make a fit to the stellar continuum, which is again from MUSE, and we use different templates to get a fit in different bins, which actually gives us the stellar kinematics. And for this, we use the GIST pipeline. Okay, so now bringing you to the results, what I want to show you now is in the first column, the stellar kinematics, in the next, the ionized gas kinematics from O3, and then finally, in the third column, the residuals, which would show how the ionized gas is behaving when the stellar contribution is removed from it. And always on the top row would be the velocity, and on the bottom row would be the velocity dispersion. So as you can see here, here is the stellar velocity, and below it is the stellar velocity dispersion. So quick conclusions from this is it seems to be a nicely rotating galaxy with a nice stellar disk. And in the bottom panel, you can see something that very nicely stands out is this high stellar velocity dispersion in the very central regions. When we zoom into this, we actually see that the higher velocity dispersion area is also very aligned to the radio jet axis. And now this raises an interesting question, that is this radio jet axis actually causing this as a positive feedback? That is it while its propagation interacting with this ISM, causing it to be compressed, creating new stars with a very high velocity dispersion, and maybe in a way also contributing to the building of the stellar bulge of this galaxy. Okay, then moving on, I want to show the O3 gas kinematics. Again, from this we can see the velocity of the ionized gas shows that it's kind of following the stellar disk, seems to be fine. And in the bottom panel, when we see the velocity dispersion, we see really high velocity residuals, like, sorry, not residuals, very high values, more than 1,000 kilometers per second. But this actually stands out very nicely when we see the residuals in the third column. So now you can see for velocity, especially at the ends where the radio jet interacts with the ISM in the galaxy disk, we see very high residuals. And also for the velocity dispersion, you can see this very high turbulent gas, which seems to be in these purple bins and is very much perpendicular to the radio jet axis. So the molecular gas also interestingly shows a very similar behavior, but for now I'm just showing these plots for the ionized gas. So clearly there's something happening in the center of the galaxy, and now let's take a look at what is happening in there in a more detailed fashion. So now these are pixel by pixel plots in the very central regions for the ionized gas on the left and the molecular gas on the right. Now, interestingly, for both these, you can see there is this very turbulent broad emission in both these gas phases. For ionized gas, this seems to be extending to almost thrice the distance as for the molecular gas. And also for the molecular gas, it seems to be only on one side. And another interesting thing is that the velocities or the higher velocity dispersion is about more than 1,500, is close to 1,500 for the ionized gas, but only about 500. Well, not only, but the highest values is about 500 for the molecular gas. Now, this is interesting that it's 3 times faster for the ionized gas, but it kind of also makes sense because the molecular gas would be more dense and hence a bit more difficult to move. Okay, then now moving on, let's make a comparison of this with a snapshot from the JET ISM simulation. So what I introduced initially, I come back to this in order to check what the observations look like in regard to this. So on the left, you can see we are actually looking at a snapshot of the simulation from the edge-on side of the galaxy. So basically, the galaxy is in the XY plane, but we are looking at it from the XZ plane, and hence you just see the edge. And as you can see, the white contours is actually tracing a radio jet, but it's quite inclined into the galaxy disk and hence causing this very nice interaction. And there is this very high turbulent gas that is being emitted from the galaxy, which can be seen with these reddish pixels. And a similar thing is shown here on the right, which shows the density evolution of the jet kind of trying to escape from the galaxy disk and pushing through the ISM and really escaping as biconical outflows. So what is actually happening is that this inclined radio jet is growing in a bubble of plasma. And this jet and the plasma is extensively reacting with the ISM in the galaxy. Now, because of its inclination, and the interaction is strong, and this is causing it to want to escape from the galaxy. Now, in order to escape, it chooses the path of least resistance, which is the perpendicular direction, and hence is something we see as these biconicular outflows. A very nice way to see this is maybe through this schematic, in where we show on the left side the galaxy just as how we see it, and on the right side an edge-on view. In both these plots, the gray is the galaxy disk, and this black structure that you see in the center is the low power radio jet. So as you can see, where the radio jet is actually hitting the ISM in the galaxy, there is also some velocity enhancement seen, which we mark through these red and blue features, and we see these significant jet ISM interactions here. And as this bubble of plasma grows and tries to escape, it's very nicely visible through the right side, the edge-on plot, that it actually escapes from above and below the galaxy in these biconical flows. Having said this, I want to bring you back to a look of the literature. So this turbulent gas escaping perpendicular to the jet is something that's also seen in literature for the Seyfert luminosity regime. So all these targets that I plot here. But the target that I just showed you lies in here, which is actually the quasar regime. And the other targets that we would like to study also fall in this slight category of the quasar regime, which I have plotted separately here. Now, the idea is, why is it so important to focus on this, is because since these are quasars, there's this very strong accretion happening in them, and hence maybe the intuitive prediction would be that outflows would be caused by accretion disk winds. However, we see the low power radio jet also causing outflows, and this then becomes a very interesting question to kind of try to fill this parameter space by all of these targets and understand how important is this effect for the quasars. And this is what now we are trying to do by studying all these targets in a similar approach. So we already know for all these targets from a previous study for the ionized gas that like here I'm showing the data for velocity and velocity dispersion for 10 of the galaxies, and all the contours here are the radio contours. So we kind of already know that wherever these contours hit the ISM, the galaxy ionized gas, there is something special happening. So there are some special features you could clearly trace in here. But now, interestingly, along with ionized gas, we also have the data for molecular gas and for stellar kinematics, which gives us a great comparison and would try to answer a lot of questions and reveal some great results. So this is what I'm briefly showing here for what we are doing now. So in the top panel for all these galaxies is just a snapshot of the stellar continuum. Then in the next panel is the O3 emission for all these galaxies, the same galaxies. And then finally, what we have is the CO3 to 2 transition from ALMA. So as you can already see, all these, even from the first look, like morphologically, have something very different going on. And this would be super interesting to kind of compare them and see how is the jet affecting these. For now, I'm just showing these very basic plots, but I would be happy to show very, very preliminary work when we are in the discussion. Okay, so with this, I would actually like to conclude the talk with the main conclusion. So what we are saying here is that locally, we actually see the jet to be causing great interaction with the ISM in both the ionized as well as the molecular gas phase. Then we also see this multi-phase turbulent gas, which is being driven perpendicular to the galaxy by this low power jet. And this is something that is way more extended and stronger for the ionized phase. And then finally, we also see a spatial connection between the jets and the stellar properties in the very interior sections of the galaxy, or by which we predict that maybe there's also some positive feedback happening there. So the last message that I want to drive away home with you all is that even though the radio jets are low in power in these galaxies, they could still have a very strong feedback on the quasar host galaxies, and hence it should not be avoided and should be studied in detail. And with this, I would like to thank you for listening, and I'm very happy to take questions now.
Excellent. Thank you very much, Aish. That was a great talk. So for questions, I think we'll start with Paula.
Hi, Aish. Very nice talk. Yes, I have several questions. I try to keep myself very short. First, your results are based deeply on the goodness of the subtraction of the stellar emission, the stellar spectrum, right? Mm-hmm. Because, yeah, you want to extract only the effects of the AGN on the oxygen 3 lines. So how good is it? Can you estimate an error bar there? How is 20%, 10%? Because at the end of the day, you base, all your results on the kinematics of the oxygen 3 and the CO3 to 2 due to the AGN only.
Yeah, that is correct. We are actually trying to make the observations. Sorry, I think I just skipped the slide. Yes, here. The observation for O3 and CO independent of stellar. So we do have some error bars there, but they are quite small. So for example, when I measure a velocity of about 250, it's the error bar is about 16 kilometers per second. So percentage-wise, I think this amounts to about like 10%.
Okay, can I ask a second question? I don't know.
Yeah, sure, for me.
The CO322 line, right? You may miss a lot of gas, right? Because you only have one configuration with ALMA and so on. You should make an extensive searches of diffuse gas. And so it looks like it's, it looks like it's not much molecular gas there, but I didn't get what is your conclusion on the host galaxy because of the distribution and kinematics of the CO322.
So what I didn't talk about here is also like we tried to do some energy estimates using the molecular gas, and then this broad component that we see in molecular gas, we try to understand how much energy this has, how much energy it contributes to the ISM, and as compared to the jet power, and how would it be able to kind of escape from the galaxy or not. So our understanding from this is that it will not escape the galaxy because the energy that the jet imparts onto this gas, onto this turbulent gas, is way less than the, well, not way less, but an order less than the binding energy. So at some point it's gonna fall back. But however, we, of course, like, we don't believe that feedback is only removing the gas, but it's also making the gas turbulent. So it's anyways becoming turbulent and may not be available for star formation. And going back to the first part of your question, yes, we did think about this, that maybe we are losing out on some flux because of the different configurations. So we try to take like a scaling in which we seem to gather like the most of the flux, and we have most of the important areas covered.
Okay, thanks a lot.
Do I answer your questions?
Well, we can discuss offline, don't worry. Go ahead.
Okay, great. Thank you.
So I actually have a question as well. So this is about the stellar template fitting that you did. So I was curious whether you had enough signal to noise to then study the stellar population in these different Voronoi bins and see whether in these bins, perhaps, like as you, I guess, plotted perpendicular to the jets, whether you would see perhaps a different sort of population compared to in other parts of the galaxy. Was that something that was possible or tried?
So all these regions, the bins that you see here, they are Voronoi bins, and they all have like a signal to noise ratio of 30. And we also make a exclusion of all the regions that are less than, all the pixels that are less than 3 signal to noise ratio. So like going by the signal to noise, I think we have very nice data, but also to make sure that like we are not, we don't get like widely different results. We try to make these fits for every bin using kind of different wavelength ranges in consideration, and also changing the masking that I show here in the bottom panel. So you can see like we try to mask the emission lines. So we try to make these maskings like broader or lesser. So in order to make like the contribution of the fits, contribution of the data to the fits change. And then we make this comparison to see like how much is the estimate changing. So basically the estimate is not too different, and hence we can be confident about the masking we use, about the amount of spectra we have remaining, and definitely the signal to noise ratio is already good enough.
Okay, thanks. And I guess, did you see in any of these fields, because I guess at high redshift, sometimes we see ionized gas like nebulae surrounding these quasars, or even in molecular gas. Did you see any of that, some extended emission away from the galaxy itself?
So we see this companion galaxy that you can see here. Well, we call it companion galaxy, but maybe this is like a extent, so the redshift for this, and it's definitely interacting with the main galaxy, as you can see here. But I mean, like I think if I understand what you're asking, the perspective of your asking is to kind of trace the circumgalactic medium, right? So there are like these two satellite galaxies, and the bottom one of them is visible here. And there's this other one, but we don't study it because we were looking more into the galaxy than the CGM. However, if you're curious, the data is online, and feel free to, you know, like study the CGM using these.
Yeah, great. Giacomo?
Yeah, sorry, thank you. I'm sorry because it's not my field completely, so it's more for me to understand more than, you know, a question. So sorry also for the participant. But I was looking specifically your first result. You mentioned clear signatures of impact of ionizing gas on ionizing gas and molecular gas. But when you say in clear signatures of impact, so I was wondering what does it mean in terms of quenching or accelerating star formation? So just what does it mean impact exactly?
So what we are saying here is any sort of impact on the galaxy, like the feedback can be in various forms, that you're maybe disturbing the available gas, and hence the gas cannot form stars. It's not cool enough, it's turbulent now, and hence it cannot form stars. So this is a sort of a negative impact. Or maybe the other probability is that you remove, like the jets can be so powerful that they can actually remove this gas, which is something that we actually see in our galaxy. But this is not so much high in energy, and the binding energy is still higher, so it would somehow fall down. But if you see the different time scales, it would still be an amount of gas that would be missing for the stars to be formed. So this is still an impact on a negative impact on the star formation. Okay. But we are also saying that we see a positive impact in these very central regions. And sorry for going on and back and forth in the slides, but like in these very central regions where we see this higher velocity dispersion, one explanation for this could be that the jets are actually compressing the gas clouds there, and this compression is causing more star formation, which is aiding into the formation of the bulge and is giving this very high velocity dispersion. Okay, but this but these different behaviors or different, you know, this also depends on the environment in which the clusters, the galaxy are, whether they are clusters or whether, or it's just really completely, you know, a galaxy business, basically. So yes, of course, the environment of the galaxy would affect it for sure in many ways, depending on how heavily it's surrounded by other galaxies. But like this is also something that needs to be excluded, like mergers and effects due to mergers need to be excluded before saying, this is something that's because of the AGN. For example, for our galaxy, since we see like such ordered stellar rotation and also ordered molecular and ionized gas rotation, we think that it's not affected by mergers. Okay. Okay. Thank you. Thank you. Okay. And congratulations. Thank you.
So let's thank Aisha again. It was a fantastic talk.
Thank you.
And I'll hand over to Joshua and Nicola for the next half.
Great. So Nicola, if you could share your screen.
Okay.
Okay, great. Yeah, I'm here to welcome Nicola Borghi. He is a PhD student at the University of Bologna and is interested in topics such as observational cosmology and extragalactic astrophysics. In particular, he likes study cosmic chronometers, gravitational waves, stellar populations, and galaxy formation and evolution. Today, he will talk about towards an independent reconstruction of the expansion history of the universe. The floor is all yours. Good luck.
Thank you very much, and thank you to the organizer for giving me the possibility of presenting my research. The aim of my research is to explore independent cosmological probes in order to measure and reconstruct independently the expansion history of the universe. And I should thank my collaborators, Michele, Andrea, Alexandra, Lucia, Salvatore, and Kang, with whom I published 2 papers that went out very recently. So what I mean by expansion history. So basically the Hubble parameter, h of z, telling us the rate of expansion of the universe over different cosmic times. Let me, enable this. So this is the current picture. What we know about the h of z, especially at redshift 0, is based on these 2 very precise measurements. One by supernovae, 1A supernovae, giving results of about 73, and the second one inferred from the observation of the CMB, assuming a lambda CDM model. And this gives us a number that more approximately 67, sorry. And these 2 measurements are more and more precise, and they are and a tension is emerging, a discrepancy between those 2 measurements. So we need independent probes. Other measurements can be obtained with the surface brightness fluctuation. I put here an example, or with gravitational waves, and I will discuss a little more in more detail about this. I should also note that there are many other measurements, some of them indirect as the CMB, some of them direct, for example, using the distance ladder method with the supernovae and different calibrators, for example, tip of the giant branch and so on. And if you're interested, you can have a look at this recent review coordinated by Leonardo Di Valentino. What is emerging now are these 2 different values. So it's important, coming back to our more simplified view, to explore independent probes, independent from these 2 main ones, that can be able to tell us something different about the expansion of our universe. So going at larger redshift, we have also the possibility of obtaining information using baryonic acoustic oscillation. These probes, while having their strength, relying on the assumption of a cosmological underlying scenario. In particular, BIO rely on the early physics related to the CMB. And we have also other different probes, such as cosmic chronometers, which have proven to be a very good probe to study h of z. And they are now giving most of the data points that we have in our data sets today. If I should focus on 2 of these probes, one is cosmic chronometers, and I will explain you why, and gravitational waves as a promising tool to explore the universe. So let me start by cosmic chronometers, which are the main topic of the works that I've that I'm going to present. So there are events in nature of which we do not know absolute values, but we know how things change over time. Take a look at these as slice of a tree. We can measure the expansion of a ring over a certain amount of time. Here, the accretion, let's say, of a tree is represented by this annually. One annulus represents 1 year. The bright part is spring and summer, and the dark part is autumn and winter. You can see here that at the beginning, this accretion is small, and then this rate of accretion is larger. What can we say about it is that the expansion of the tree changed over time. In particular, we are not looking at a general tree. This is a tree that survived the Tunguska event. Tunguska was a major meteorite impact. And this tree survived. And after 1908, he had more energy, more space to gather energy from the sun, and also more nutrients, since other trees went down, and so it was able to accrete more matter. This is the same concept of cosmic chronometers. So going through the equations, you can obtain this very simple formula just by assuming a relatively simple underlying metric, the Friedman-Lemaitre-Robertson-Walker. And the main idea of cosmic chronometers is to study h of z and to measure h of z using the differential evolution of a population of objects over redshift. In particular, we would like to know how the age of the universe changes over time, but we cannot directly observe it. So we make use of a homogeneous population of objects, cosmic chronometers, that are able to trace that evolution. It's not important to know their absolute age. The important is that their differential age traces the aging of the universe. So what we can do is to take this sample of objects, divide it in bins, and study the differential evolution of these t over different bins. And then by applying this simple formula, obtaining different points of h of z. These points can then be compared to models, lambda CDM and other kind of models, to discriminate between these models. So a quick recap, cosmic chronometers provide a direct measurement of h of z, no other cosmological assumption except from the metric. They have a differential approach. We don't need absolute time measurement, but differential time measurement, and they are cosmological model independent. And the main requirements that I'll try to investigate in my work is to select a poor sample of these tracers and also do accurate measurement of these DT. So best candidates of cosmic chronometers are galaxies that are very massive and passive, since those galaxies formed very early and had a very strong formation and then a decline. So they are the oldest galaxies at each redshift, and also are homogeneous in number density over redshift, up to at least redshift 1 and 2. We know that these galaxies are like that also because we studied locally their stellar population. So this red Gaussian is represents high mass galaxy. They formed in a very short time, and then the star formation had a decline, then evolved passively. And we tested this, and many authors tested this through correlation between metallicity and alpha over iron. Alpha over iron can be thought as a tracer of this star formation history duration, and I can say something more if you're interested about that. How do we measure their ages? So again, I stress that we are interested in differential age measurement, not absolute, but then we have to estimate these ages through cosmological through stellar population models. Here are different methods that can be used. Problem of photometry is that the constraints that we obtain on age are very degenerate with metallicity. You can see that this in by looking at the gray histograms here, and the degeneracy between age and metallicity. We can then obtain a spectral information. It's costly from an observational point of view, and also from a computational point of view, because fitting the entire spectrum require resources. We are expanding this analysis in a paper in preparation, in which we are studying this method and its degeneracies. Then Moresco in 2011 proposed a new method that relies on the measurement of a single index, the D4000, the discontinuity between red words and blue words, the 4000 angstrom. This index correlates very well with the age, The problem is that the star formation history and metallicity dependencies should be modeled separately. So what we did in our work was to use all the standard analysis of leak indices that are able to say to discriminate between different age and metallicity, and therefore trying to solve this age metallicity degeneracy. This was made possible thanks to the high quality of a legacy survey that spans redshift 0.6 up to 1 in the Cosmos field. So a very well covered field where we also have photometries and other measurements to compare with, and a resolution of 3500 in a high signal to noise. Problem is that if you look at this, the coverage of legacy in this redshift, we sample the rest frame band between 4,000 and 4,200 mostly. That is very narrow. We don't have much galaxies with information about their UV part and also very red part, especially here where MG index is available and can say and can discriminate even more between age and chemical content. So in our work, we focused on selecting a pure sample of tracers. We did that by combining different methodologies. So we did a cut on the classic Nuver-J in order to select galaxies that were not star forming, then additional cut in order to remove galaxies with a strong emission. It is also important to say that it's not clear if emission of O2 is produced by only young population or also all the population can have this emission, but we want to be as sure as possible. So we selected a pure sample of them, removing every galaxy with a O2 emission, and further removing galaxies after a visual inspection that showed emission line of O2, O3. By doing so, 20% of the legacy galaxies were selected as massive and passive, and they have a specific star formation rate that is usually very low, lower than the usual value that is -11, that is taken for reference for this system. And you can see here the distribution in redshift, in stellar velocity dispersion, and in star formation rate. So we developed a code named PyLeak. You can find it available on GitLab in order to measure specific indices, not only leak, but also newly defined calcium H and K indices, defined for the first time in a thesis by Valentina Fanfani. And with this code, we went through all those galaxies. First important results and trend to consider, H over K. So why we studied H over K? Because H over K can be an independent diagnostic in order to assess if our galaxies are really passive. If we start from the violet spectrum here, this is the K line, this is the H line. Going from passive to star forming, these indices lower down. At least calcium K does this, but calcium H doesn't show this trend because at some point the infill of the Balmer H epsilon line dominate. So this doesn't evolve like calcium K. We find this bimodality in calcium K at 5.5 angstrom. And in order to verify if those galaxies are really passive, we tested this diagnostic, and also found that selection of H over K lower than 1.1 can correlate very well with a specific star formation rate cut less than -11. So if we do not have a very wide photometry, because a specific star formation rate usually required a very wide photometric coverage, but only a narrow spectroscopic coverage on H/K, we can still make some selection on these objects. And this plot showing exactly this. So those are 4 well-known diagnostic diagrams, Nu/J and UVJ. You can see that H/K ratio correlates very well. This is not the case for the oxygen 2, because there are some galaxies with low H/K that have also a high O2 value. But it's very interesting, this plot that shows that that shows this correlation between H/K and the star formation rate. So going into more details relating on the stellar population properties, we use the TMJ models. We modeled these galaxies as simple stellar population. We also tested later if this hypothesis can hold. And we searched for and found an optimized set of spectral indices that maximizes the spectral coverage, but also the galaxies that can be analyzed. So galaxies that are homogeneously covered by those indices, because dropping one indices and modifying the composition of this set, we saw it later, can induce a redshift dependent bias on our results, and we don't want that, because we want to do cosmology on this data. And because of this, we also want to go beyond classical galaxy evolution studies, and we did this analysis without assuming cosmological priors. Usually cosmological priors are assumed as upper limit on galaxy ages, but we do not want to introduce cosmological prior because they can introduce bias and circularity on our analysis. We obtained constraint for 140 individual passive galaxies that have a very good signal to noise, and we found average errors of the order of 0.4, 0.5 giga-year, and errors on the metallicity and alpha over iron content of 0.05 magnitudes. So these, those are the results, usually illustrated by comparing age, metallicity, and alpha over iron versus stellar velocity dispersion. What we can say of these galaxies is that even at this redshift 0.7, they have similar properties, the similar amount of metal content as their local counterpart, here shown in gray. So we can be more sure that these galaxies actually are a homogeneous population of a redshift. This population of galaxy already exists at that redshift, and they can be used to gain cosmological information. Also, this is like a quality check that the vertical offset between these two populations is in agreement with the aging of the universe, but we don't want to use this information because we only focus on our galaxy, and we try to guess to measure h of z only on our violet points. And also these scaling relations are consistent with mass downsiding, even if the scatter is very high because of the limited size of our sample. What's important from a cosmological analysis is the age redshift relation. And we did that by binning this data. You can find here that the downsiding is even more clear with a higher, with older galaxies being more metal rich and also more alpha enhanced. With the common interpretation, alpha enhancements mean shorter star formation histories. So by using this age redshift relation, those 8 points, we basically divided this into population, higher mass and lower mass, and between two of each point, non-consecutive point, we measured a value of h naught, of h of z. Those values were averaged using a weighted average, and we finally obtained this violet point. So what's new about this measurement? By studying individual galaxies and their accurate stellar population, we were able at the same time to say something about their the galaxy evolution and their underlying cosmology. Also being more sure about the age, and since we tried the best to remove this age metallicity degeneracy. We also tested this using more extended stellar population synthesis model, but also by using different combination of indices. This is another main point that I want to stress. If we if you change the combination, the set of indices to constrain this galaxy, we can find absolute ages that vary plus or minus 1 giga-year. So a very strong variation. But since we are interested in the differential age evolution, so the slope of the age redshift relation, we found results that are very consistent between each other with within 0.2 sigmas. Yes, this error bars are very high due to limited sample, but these results saying that our h of z measurement is pretty robust against these systematic. So what can we do after this? We can combine our point with all other points and also exploit and also take advantage of future probes. For example, here, a probe that can map redshift 0.2 up to 0.7 with a much higher statistic, and also a high redshift probe that, for example, can be Euclid. By combining all those points and comparing those data with the underlying cosmology, we can gain knowledge on some of the cosmological parameters, h of z, omega m, and so on. And also, of course, the evolution of the dark energy parameter, which is very important. And this is an independent probe to test these numbers. So these are cosmic chronometers, and this is a quick summary. So what we did in the first work was to study the stellar population and their relationships and the scaling relation. And in the second work, we derived the cosmological measurement and tested different systematics. I don't have the time to do that in detail, but this analysis enabled precise study of these of all these systematics. So what's next? We can use cosmic chronometry in combination with other independent probes, because yes, in principle, one can obtain information of h naught by extrapolating these points, but it's even more interesting to combine different probes in order also to reduce their systematics. And a very promising one is gravitational waves. I'll be very quick on the physics because it's very complicated, but there is a key point. So if for supernovae we know the distance through a sort of distance ladder construction, here with gravitational waves tell us directly the distance dl. Here I put the formula. dl and redshift are related at the small redshift by this simple equation. So if we know the redshift, if we know dl, we can provide a direct measurement of h naught. There are some degeneracies to take into account, but this is a promising new probe that and I will show you basically the results. So first of all, if we measure gravitational wave, we measure dl, but we do not measure redshift. This is inside the how we obtain information from gravitational waves. But we can learn about redshift if we are able to find the counterpart, so the source or the hosting source that produced this event. This was done for one golden event, GW 17817, the only one up to now. So we learned DL from gravitational waves and redshift from the electromagnetic counterpart, the spiral galaxy NGC 4993. You probably know
Nicola, you have 2 minutes left.
Yes, thank you. All these observations that were done using different electromagnetic telescope, but the most important one is the spectroscopy of this galaxy that provided us with the redshift measurement. But what if we do not have redshift? We can still use gravitational waves, because we can cross-correlate the gravitational wave localization with the galaxy catalog. I have a very simple scheme here. So assume that we know the depth of this localization. This is the results of a gravitational wave analysis, but then we cross-correlate with a catalog. For example, we find a galaxy here, we can say something about H0, but maybe there is also a galaxy here, so maybe H0 may be also this value. Another one, and another one. So by doing this cross-correlation, we have a probability distribution of what can be the value of H0, but combining different independent gravitational wave events, we can have a measurement. And these are the results. So first of all, the gray area is the result obtained with the counterpart method, so redshift known, and the red one is the same event, assuming that we didn't observe a counterpart. So redshift unknown, but gained from a galaxy catalog correlation. Constraints are very wide, but the future is very promising, because if we see other events, especially other bright sirens, almost 20 events, we can reach percent level accuracy. At the same time, this is third generation detector. By doing by going deeper in redshift, we can also try to rebuild H of Z, not directly as cosmic chronometers, but with many events that wouldn't be a problem. So main conclusion of my work is that it's very important to combine different and independent probes. This is a forecast, an optimistic forecast, and I want to leave you with this optimistic forecast. Thanks for the attention.
Great. Thank you a lot for your very interesting talk. I really like the way you combined multiple topics and understand the galaxy, the universe in a whole. Are there any questions online? If not immediately, I will start off with one. So if you go back to your galaxy evolution cosmological conundrum plot, you had an error bar there. But yeah. Through your talks, I understood there were many systematics that could cause the error bar. So I actually just wondered what dominated it. Is that just a sample, or is the one or specific systematic?
It's a different combination of systematics. For example, this is one of the most important one. So changing the stellar population synthesis model. I said that we assumed simple stellar population. Simple stellar population means an instant burst, and then the star formation stops. And we tested also with other models that assume a wider star formation history. So this is, for example, a plot that shows that this degeneracy. So these two best fit, let's say, are very similar with respect to the observed, the spectrum in gray, but their the tau age degeneracy here is very clear. So we repeated this analysis, testing different stellar population synthesis models, in particular this one by Vazdekis 2015. We also changed the binning scheme that since we have limited statistics, is another source of systematic uncertainty, and also included the difference of varying the indices, as I showed in the in that slide. Sorry, this one. We varied the combination of spectral indices, and we obtained very consistent result, but added that contribution to the systematic uncertainty.
Okay, thank you. Okay, if there are no more questions, people know how to connect you, so I give the floor back to Giacomo.
Hi, Josh. Yeah, thank you very much. Thank you, Joshua, and to Simon for chairing the session, and congratulations to Nicola Aish for the talks and for being selected. And I wish you all the best, of course, for the coming month. And hoping we are gonna see each other in real life soon at ESO. So with this, I would also thank the people who attended the talks, and I guess see you in a week. Bye-bye. Thank you.